Hello and welcome to the AC260 lab. Today's topic is Lab4 transformers. This is the second time I try to record this. Let's see if this time it goes well. It didn't go well with the online meeting. I'm sorry for that, for all the people who got affected and for the waste of time. So the goals for the lab are, well, find model parameters of a single phase transformer. We are not using the three phase for this lab. You're going to derive models and use them to interpolate along your collected data or given data. This is pretty much the same thing you've been doing for lab 2 and lab 3. We are extending that to lab 4. So nothing new, nothing that you don't know how to do. And of course, we're going to answer questions. You're going to answer questions about transformers. There are multiple choices, and there are questions for which you have to type some text. The Lab4 submission, as usual, is just the answer spreadsheet, which is the method we've been following since lab 2. And of course, as usual, I'm going to go and give you tips about how to use PSIM in this lab and answer the questions in the spreadsheet, what you have to look for, and be mindful when you are solving the problems. So let's get to PSIM first. So PSIM, there are not many files for this lab. So we're going to rely a lot on given data that we have collected in the lab. And the reason for that is very simple. The transformer model in PSIM cannot be saturated. And because of that reason, it's pretty much just the linear part of the transformer what is modeled by PSIM, and that does not allow us to really get all the features that we want to show you in the lab. Therefore, we're going to run a few tests using simulation, but some other stuff is going to be covered with actual data that we've collected in the lab. So the first circuit you're going to be using is an open circuit. So you're going to run the open circuit test. And what you need to understand about the open circuit test with PSIM compared to what you would do in the lab is that we need this bias resistor here. So in the lab, you can leave these terminals open and connect the ammeter and voltmeter here and do the measurements, and it's going to be fine. But in PSIM, we need to put something that will bias this. So there's going to be a very, very small current circulating, but that will allow the tool to compute the values for the rest of the circuit. So keep that in mind. That's one of the limitations of simulations. So you need to sometimes to do crazy things like this to be able to simulate the circuit or the device. So what is going to happen is you're going to simulate this thing. You're going to collect IOC and VOC. Everybody is going to get a different set of values, because when you go to the spreadsheet, you will see that once you pick your group number, you're going to have to change the parameters inside the model. So let me bring the model window here. So this is the model window for the properties for the transformer, and you're going to have to change these values in here depending on your group number, and that is going to give everybody a different set of values for this simulation. These numbers that you're going to input for the open circuit test, you're going to have to also change them for the short circuit test. So keep that in mind. That's important because it will give you the different results that we're looking for. Now, for the short circuit test, for this one you don't have to do anything. We already put here the value that you need, the peak amplitude that you need to have, and the frequency, so you don't have to change anything in here. Now except of course the values for the properties of the transformer, the parameters of the transformer. Now when you move into the short circuit test, now you have an ammeter here that is effectively short circuiting the secondary side of the transformer, and what you have to do is you need to change this peak amplitude here, usually starting with a small value, and simulate until you see the nominal current for the secondary circulating on this short circuit so on the secondary current. Once you achieve that goal, then you take the measurements for the short circuit current and short circuit voltage, and of course you're gonna need the power too. So when you simulate this, let me show you. When you simulate this in PSIM, you say I want, so let me bring the window here to where it's recording, and we need VSC, ISC. So VSC, ISC in one window. Now the window is here, and we need to split this and add IS. And so what you need to do when you click in measurement, what you need to find out is, let's put the cursors in the right positions as we know we should do, covering as many cycles as possible. And so what's going to happen is that you're going to change the value of the voltage until you reach your nominal current. The nominal current doesn't have to be perfect. It could be a few milliamps more or less, it doesn't matter, but close enough. And then what you do is you collect the RMS values for the voltage and the current, and you can also read directly from here the power that you are going to need in your table in the future. So that's all you have to do for the open circuit and short circuit tests. In both cases, of course, you're going to have to collect this power. But in the open circuit test, you don't have to measure any current in the secondary or voltage in the secondary. You just need to have there the VSC and ISC. Now let's move to the other two circuits. So there are two more tests that you're going to run, and those are the polarity tests. And from this schematic here, you can see that the second one is exactly the same. So I'm just giving you two versions of the same thing for convenience. So what you have to do here is you need to wire up one of these as additive polarity and the other as subtractive polarity. So that's a concept you've studied in class. You can go to the book and find how to do that. But basically you need to add connections here. So one of them is additive and the other has subtractive polarity. Again, these two resistors here are biasing. So they are very large. So they're basically no load for this transformer. They are not going to affect the behavior of the machine by having these two super huge load resistors, which are very, very small loads. And so that's something that's sometimes confusing. But keep in mind, the bigger the resistor, the smaller the load, because the less current it can flow through it. So now, what's going to happen is, well, you're going to fill up the table for the additive and the subtractive versions of the connections of the independent windings in the secondary, and of course you are going to answer questions about that. So keep that in mind. It's just for convenience the way we put this in here. Now that's everything about how to simulate this. Of course I'm not going to simulate this one because I would have to make the connections, and I don't want to do that because that would be the answer to the problem. But keep in mind that what you need to do is just to run these 4 files. There isn't going to be a lot of work in that area. Like I know sometimes simulations are time consuming because you have to change something, click, wait, and record. Anyways, all that. Now let's move on to the template. So the template is kind of familiar format that you know. You need to choose a group number. I'm going to choose 13 here, and it has the goals of the lab and all that. So the first section where you have to do some work is section 2, and in this case we're giving you a table of nominal values for one of the transformers in our lab. So we're giving you the volt-amperes with the voltage of the different windings. These are nominal voltages. So basically, the way you collect this information is you go to the lab, you get the transformer, you look for the plate on the transformer that has all the nominal values, and possibly sometimes it doesn't have that, but a good transformer should have a table telling you what are the terminals for the windings and so on. So what you do is you collect all this data and you bring it here, and from that data you're gonna have to answer questions. So we did this work for you already. So basically you need to find out how many 60-watt incandescent light bulbs you can power with the transformer as a whole, and then you need to find what is going to be terminals for this bulb, and what will be the current drained or taken by the load when you do these two possible connections to the transformer. You need to find the current. So for then we have a question related to the winding resistance. So basically we're giving you here, this is a mistake, this is a typo, I'm going to send a note clarifying this, but basically what we have here is a high voltage winding and the low voltage winding, and we're giving you the ohms, the resistance in ohms of those windings, and you have to answer these questions. So this is high V winding. I'm not gonna just submit a new template just for you to fix this, because I got the feedback from the meeting that it is annoying, and I understand it's annoying. So so what you need to find out is the reasons why these things are they're different for a reason, and you need to choose the best answer to answer this question. Then there's a question related to what happens when you excite a transformer with a DC voltage, and be careful here because you may choose the wrong answer. Like, also applies to this, to any kind of multiple choice question. Sometimes we put statements that are true, but they are not a whole truth. They might be incomplete, and that is for you to sift out and get the best possible answer. There's just one best possible answer. Even though others might seem correct because they are true, they might not be the complete truth. Okay, so be careful with that and pick the right answer. Now, the saturation test. This is the first test where we can't use PSIM to do the simulation, and the reason is very simple. We can't saturate the transformer in PSIM. So we're giving you the measurements and the plot of saturation, and what we want you to do is to find for what values the transformer starts to become saturated. So you have to choose 2 points here. So between this and this, or between this and this, or between this and that, it's up to you to pick which one is the best result to consider that the transformer is starting to saturate. And the reason the transformer starts to saturate is what is going to give you the best point, 2 points in this curve where you can consider the transformer is starting to saturate. This is the polarity test question, like I mentioned in PSIM, in the PSIM demonstration. Is you need to wire one of the circuits as additive polarity and the other as subtractive polarity. And what you need to do is to take measurements for the current, the voltages, and the addition of both voltages, which you can do in PSIM by using the composite function when you run a simulation. Let's do that with another of the circuits. So let's say this. Let's assume. Let's just think about that. Let's think this is that I'm interested in knowing what is the sum of the current plus the voltage, which doesn't make sense, but it will serve this demonstration. So when you click in PSIM and you see this dialog here that shows you what functions you want, you can say I want IOC, and I'm going to add to that VOC. The tool doesn't care, and then you click on in add, and you have here in variables for display IOC plus VOC, and when you click OK, it will compute that and show it to you. And that's the way you get E2 plus E3. If you didn't know that, now you know. And you have to put these two values here, and of course then answer these two questions. Remember, these questions, you don't have to write too much, but please just read it carefully. Don't try not to repeat yourself multiple times. Try to be short but precise. That's what we want, and it's a good skill to have in engineering. So you should try to be succinct, but at the same time you should be as precise as possible. Now, for the open and short circuit test, you're going to run the open and short circuit test like I said before. These numbers here will change depending on your group number, and this cell in blue is the nominal current for the secondary winding. And so what you're going to do is you're going to put these numbers here. You're going to take these numbers from here, put them in the change the transformers parameters to match this. Be careful with this magnetization inductance because it's in henries. These are in millihenries, so don't get caught up by this. And now what you do is just, of course, go simulate that circuit, and you get the voltage, open circuit voltage, the open circuit current, the open circuit power that you could measure using the measuring window. Then you need to find the you need to find the cosine of theta, which is basically the power factor, and this ratio, and then the angle in radians, and from the admittance you need to find the real and imaginary part because it's a complex number, and from that you're going to find RC and XM. There's an example in the book that walks you through this process. So the book here is very important. Just go get the book, read the book, find the example where they compute these two parameters for the equivalent circuit from the open circuit test. And keep reading, because after that you're going to find the example for the computations that you need to make to compute the other parameters that are related to the short circuit test. And then you have these questions here that you may think they are pretty much the same as in the next section, but they are not. Why? Because you need to answer these based on the test that you are conducting. So what are the power losses that occur in the open circuit test and why? Right? And the same goes for this one. If you were a transformer designer, what would you do to reduce these losses? So this is related to the open circuit test. So every question in this section, even if you find a very similar one in the next one, they are different. So you need to focus particularly from the perspective of the open circuit test. What are the losses? What can I do to improve the transformer? If I were a designer, which losses don't change, and what would happen in this test if I just apply more voltage, for example. Now when you change to the short circuit test, your circuit has changed completely, because now what was open and didn't have any load, now it's short circuited. So basically has the maximum load that you can put in it. And that's the reason when you run this test, you need to start with a very low voltage value in the short circuit voltage, right? So the source has to have a very small value. In the lab, you need to start this test with the knob of the power supply at 0, and there's a warning in the lab manual. If you don't do that, you can burn the transformer. And so you start from 0 very slowly until you read the nominal current in the secondary approaching, so the current that you measure approaches the nominal current. And then when you reach to that point, then you come here and you take the measurements for the voltage, the current, the power. Again, you need to compute the power factor, you need to compute the angle, and this ratio here. Just look it up in the book, and then you need to find the equivalent resistance and the equivalent reactance. And then again, you're going to answer questions very similar. There's another typo here. That's me copy pasting. And of course, these seem to be the same question, but they're related to the short circuit test. Okay, and so then you go and find the transformer regulation. So what do you need to do for the transformer regulation? Of course, you're going to measure what is going to be. You see here the load is very high. We're going to measure here what is the voltage when you have no load. So you don't have to change the input voltage, but then you need to change the load that you connect to the circuit. So you need to modify the open circuit test. Right now you're going to add a resistor and a meter and a voltmeter on the secondary, and from that you're going to fill in this table. So you don't have to change anything else in the circuit except you don't have to change anything. And what you need to do is to record these values, change the load that you put in. So that resistor that you added on the secondary, you need to change it until you see this secondary current flowing through that resistor. And at that point you have the load, you have the voltages, and from that you compute the voltage regulation. And of course you need to write here the equation. Now for the load test, this is our test we can't run in the lab, with simulations. So we're giving you a bunch of measurements from the load test. So basically we're changing the load on the transformer, and we're recording the current in the primary, the voltage in the load, the current in the load, and from that we get the power in the primary, the power in the secondary, and the efficiency. And so this VP here is the source voltage. Now with that information, we're plotting this blue line here, and as you can see is linear, because we are working in the linear correct part of the characteristic. But you're going to have to create a model, and of course whenever you have this, you can always fit the linear model. You don't have to find complicated circuitry models to model the device in this region. Unlike previous labs where you worked with simulations and this was a really straight line, here you can see that there are small measuring errors, and that's why the blue line is not perfectly straight, but it's fairly straight, so we can approximate it with a linear model, and that's what you're going to do. So in a real lab, this is what you would get. With simulations, they turn out to be much more pretty. And of course you need to compute the values, and remember, you can watch the video and get the numbers, but we want to see the equations here, right? So no equations, no marks, and that's what we wanted to see. Now then there is the efficiency model. This is the trickiest of all. Okay, this is the trickiest of all, because as you can see in this table, we don't have any way from which we can compute the parameters of this transformer to get the equivalent circuit, and so we are pretty much in the dark. But under some assumptions, we can nonetheless create a model to plot on, to interpolate on these measured values. So and so this is the efficiency characteristic. So what we're seeing here is, in the x-axis is the load current, and in the y-axis is the efficiency. And what this tells us is how efficiency changes as load current changes. Okay. And so this is very important because it allows you to feed a load that would improve the efficiency as much as possible, so you have the minimum amount of losses when the machine is operating. Of course, you know the loads are going to change, but the best position you put this in real practice, when you are deploying a transformer, the less losses that you have. And that's important for everybody, because as a user you pay less. As someone who generates electricity, you make more money. So now what we need to do here is find a way to get this orange curve here. So one of the first things you need to do is to find the copper losses at no load, and there's an assumption from which we can do that, right? And so you need to find the PCU at no load, and these hints are very important. They are critical. They are going to help you figure out how to proceed with the rest of it. And the reason for that is because, you know, the copper losses, they are variable. They change when you change the load, and the currents change, they also change. But we don't have the resistance of the secondary and primary, so we can't really compute the power losses. But under the right assumptions, we can indeed find P-core and estimate that value as a midpoint in between two different points of this curve on this table, and that will allow you to compute the power losses, the P-core, incorporate this value in the equation, and get the efficiency. And it's of course an approximation, it's not exact, so there's going to be some difference when you compare this to the equations you've studied in class. Remember, in Lab 2 we have a similar situation. When we tried to make the linear model, we had to add the current in the motor when there was no load, because still there was a small current there. Something similar is going to happen here, but you have to figure out this yourself. The good thing is that once you have this showing up this way, you are done, because you know the way you are computing the values for the efficiencies is the correct way to do this. Remember here, you can always come and copy these numbers and paste them here. If we want to see the equations, we're going to check that you have a formula on the cells to do the computation, because we can randomize this table and give everybody a different data set. So you're going to share this. Please be responsible on how you do that, because it's very important that you try this yourself and you learn something from it. This is everything about the lab. The lab is not very long. In my opinion, is easier than Lab 2 and Lab 3. Lab 5 is going to be more complicated, but this one you should be able to complete very quickly. If you have any question, you can send me an email. You can post your questions on Piazza. I will address them there, or by email. I prefer Piazza, of course, because everybody can benefit from my answers. If you need to talk to me, just contact me. Don't hesitate to do that. We will set up a meeting and have a conversation and have a talk about what you need to do, etc. Thank you for your time. Work on this lab as you've been doing in the previous ones. Most lab reports that I'm reading are really good, so keep the good work and good luck with this one. Thank you very much and have a great time answering this lab.